All right, let's consider a car turning around a corner. It's an example of circular motion, of something going in a circle. So let's consider this car. Let's imagine that it's going this way at some initial velocity at 60 kilometres an hour. Now, it doesn't change its speed, so its final velocity vector is going to be the same size, and it's going to be going at our final velocity v after it's turned through 90 degrees and then might continue on its way. But during this time, it's undergoing circular motion. So if we do a vector sum, we can add them. If you remember how we do vectors, we add vectors by drawing them tip to tail, one after the other. But let's just stop and think about acceleration for the moment. Acceleration is the final minus the initial. It's the change in velocity. How do I do a vector sum of v minus u? Well, I can only add things when I do vector sums. So the way I'm going to do this is I'm going to add minus u. So this is v plus minus u. Minus u is in the opposite direction. So this is really v minus u. And if we look at the resultant, which is from where we begin to where we end, we can see that the v minus u, that's what this is, v minus u, the change in acceleration, the direction of the change in acceleration is towards the centre of the circle. In other words, when you're travelling in a circle, you're always accelerating towards the centre of the circle. And if we think about F equals ma, therefore the force is always towards the centre of the circle. So a car, when it turns its tyres, the front wheels like this, they're going to push outwards on the road, and because of Newton's third law, every action has an equal and opposite reaction. The road's going to push towards the centre of the circle for the car, accelerating, forcing the car to go around a corner. Okay, so let's have a go at this example over here now. We've got our car, so of course we're going to remember our summary step, remembering our scaffold. We've got our car. Let's see if we can summarise what we write about our car. Well, the mass, that's already in kilograms, 1,200 kilograms. Now, what about our velocity, our speed? Okay, so the radius is 20 metres. That's in kilometres an hour, so I'm going to want to convert that into metres per second, and the way that I'm going to do that is I'm going to divide it by 3.6. So if I go, I've got 60 kilometres an hour divided by 3.6. Okay, so it's, oops, let's try that again. It's 60 divided by 3.6 is, so it's going at 16.7 metres per second. So I can say U is 16.7 metres per second. And I want to know the size of the friction force on the front wheels causing the car to turn. So it's the friction that's creating the force. It's the friction that's giving rise to the centripetal force, the centre-seeking force, causing it to go in a circle. And I'm simply, there's my law. So I've now done my summary step. So here's my car turning through its circle, and I'm trying to find out what's the size of the centripetal force there. And I can very simply just substitute this in. It's 1200 times 16.7 squared divided by 20 metres. If I grab my calculator out, there I've got 1200. Just going to move it up a little bit so I can get my zeros. Times 16.7 squared divided by our 20 metres gives us 16,700, we'll call it. Okay, 16,700 newtons. So there's the size of the friction force forcing our car to turn around a corner.